I'm going to begin now. This talk is called Unlock the Lock, Mastering Python Multi-Threading. So I want to get a sense of the experience here so far. How many people have used multi-threading in Python before? And how many of you have faced deadlocks? Nobody? Yeah, usually you face this problem, you just say, let ChatGPT rewrite this, or never mind, let my senior colleague do it. So there's nobody to help me in my company here, so I gotta figure this out. Right. Here about me, I'm working in a tractor company. They're selling electric autonomous tractors, headquartered in the US. They have offices in Singapore and India. I love communities. That's how I started learning Python from an online educator called dataquest.io. And in the past, I used to teach boot camps, but recently, in my current job, I was too busy to do that. So Lewagon is a adult career transition boot camp. I write a lot on Medium and FreeCodeCamp. FreeCodeCamp is very recently the first book I published there about logic of testing. So if you like to learn about logic and how it applies to software, you can read that. Medium, I've been writing for the past 6 years, trying to write more now. I will create a written form of this talk after the talk, probably 2 weeks to 4 weeks later. Some of my hobbies there, and then my LinkedIn is in the QR code. The code of this section is shared on GitHub already, and after that, the slides I will save as a PDF and put it on GitHub also. So if you don't know what is Deadlock, I think this is a really funny meme. This is a hiring situation, and then it just answers with the opposite question. Right, so this is a short intro. There are many types of deadlocks, but we don't need to go into that much depth. So my one-line definition is that two different parts of the program are trying to fight for the same resource, and both of them are waiting for each other. So both of them don't want to let go of what they have, but they want to get what each other has. So the whole program can proceed. So here today, what we're going to learn, we're going to learn how to use the VS Code debugger, how to step through our code. We're going to use a few buttons, F10. Usually start with F10 because you don't know where to put the breakpoints. So you step one by one and find out how the code works. When you face a function, you want to F11 to go in deeper into the stack. Once you've seen enough, shift F11 to get out of the function. And then you do this a few times, a few iterations. You know what's going on already. Now you start putting breakpoints, and then you F5 to jump between the breakpoints. So no more F10, it's faster. So one F5 equals to many F10s. Then I'm going to show you a slide about the deadlock spectrum, meaning it's not just no lock or lock. You can think of it probabilistically from 0% to 100%. And I'll show you some tweaks to make it go closer to 0 or closer to 100, or definitely 100%, or very close to 0, but I can't confirm it's 0. So if anyone has experience, you can tell me how to make it go 0. There is also a Heisenberg. It's a wordplay on the term Heisenberg uncertainty principle. So that is the underlying principle under the observer's effect. Means if there is something that is there and you try to look at it, it disappears. So that's something we'll talk about, and that makes it really difficult because when you run it versus when you run it with a debugger, the behavior is different. So you have to know what's going on if you want to fix this. Then practical uses of nested parallelism. So this whole problem that I'll be talking about stems from trying to start a thread pool inside a thread pool. And usually you don't want to do this, but there are practical reasons why you want to nest a thread pool inside a process pool, or a process pool inside a thread pool, or process in process, thread in thread, the 4 permutations for that. And also general computer science concepts that you can learn from going through this exercise. So practically, no one's going to write the code like this, but through all these debugging exercises, you can transfer this knowledge to help you learn other theories better and solve other problems better. Okay, prerequisites that we should have. If you don't have this, I will give a short introduction to each of them. So firstly, multithreading and preemptive multitasking. Multitasking is a general term of doing multiple things at once in a computer. There is 2 versions of it, or 2 types. One is cooperative, one is preemptive. The one we'll talk about today is preemptive. If it's cooperative, that is under the async IO side of Python. So you can go Google that. Under preemptive multitasking, we have multi-threading. I won't talk about multi-processing today. So multi-threading is usually suited for IO-bound tasks. So you have input-output work. It can be done faster by having multiple threads do the IO simultaneously instead of one by one. So scraping websites, sending a whole list of URLs somewhere is a common use case of multi-threading. Okay, nextly, you want to know what is blocking and non-blocking. Blocking means there is something that prevents your code from moving on to the next step. So usually this is because of this thing called lock. You want to get a lock. So when you call lock.acquire, if someone else is holding the lock, then you got to wait, possibly forever, until the other function or other object releases it. So that's blocking. Another scenario of blocking is in queues. So if you do a queue.get and there's nothing in the queue, it will block until there's something to get. Also, if you try to put something in the queue and the queue is full, it's reached its max size, it will block also. So these are real-life scenarios of blocking. Locks, I've spoken about it a bit before. So it's you want to use a lock to say that I am going to edit this memory location now, so other people should not touch this location. And after I've done with the memory location, I will release the lock, and then someone else can get this lock. So that's how locks work. And it's under the theory called synchronization primitives. And sometimes you hear the word mutex also, mutual exclusions. That's a specific type of synchronization primitive. So those are the hard skills. Soft skills, attention to detail, really have to pay attention here. Curiosity to ask a lot of questions, because I won't cover everything. So as you go back, you look at the slides, you probably find loopholes or some gaps, then I would love to hear your feedback on that. Biased action means try it. If you think, what if I do this, I do that, just try to go into the corners of the code, add some lines, delete some lines, change the seconds of how long you sleep. Those are some of the things that you can tweak. And then comfortable switching between certainty and uncertainty. This means that you do not fully control your code. When we talk about preemptive multitasking, that means the OS, as and when it wants, it can switch you from the main thread to the child thread, or from the child thread back to the main thread. There's no way to predict when that will happen, but we can try to figure out what is happening at any moment to help us reason about what is going on. Your worst case, you don't understand this talk at all, but you'll learn something about VS Code debugging. And my worst case is, you can see that there's something that shouldn't lock, but it locks. So let's see what happens. Okay, 3.1, this is the map. I wouldn't spend too long going through this. It's just a whole list of words that probably don't make sense at all now. Let's go on. 3.1 forward, PEP is a Python enhancement proposal. I think this screen is too small, so I will get out and go to the actual PEP. Python enhancement proposal. This is how core Python developers discuss how to improve existing features or propose new features before they implement something. There are many PEPs starting from number 1. Specifically this one, this was the one that triggered this, or gave the inspiration for this whole talk. So you can see that this is the problem that we have, that the whole talk will focus on this today. I will explain a bit of this code here right now. Later we'll go in more detail on this again. So you don't read the function first, you read the last 2 lines first. There is a ThreadPoolExecutor that is created with max workers equals to 1, and this number 1 is a huge problem. It's the main problem. It will be one of our solutions later. We'll be targeting this 1. When you create a thread pool, it will not create the workers first. This is different from the process pool's behavior. It will wait until there's something to do before this worker will be created. And we'll see that later when we are running through the debugger. Second step, there's this executor.submit. So this API is a non-blocking submit. It puts a certain piece of work, usually expressed as a function, onto a queue. And if the worker is free, it will take this function from the queue and work on it. Right, so certain keywords I mentioned already. There's a worker, there's a queue, there's a submission. These 3 are very important to be clear of. So what is the function here? This is the wait on future function, and it's doing something strange here. So what I want you to notice is that it is doing another submit inside the submitted work. What the function is doesn't matter at all. Power is just one of the built-ins. You can put anything here, you'll get the same behavior. The key problem is it is reusing the same executor. So this will be another solution later. That's a problem. What is f.result? F.result, okay, before I go to f.result, what is f? So f is returned by this executor.submit. It is called futures. So futures is a particular object in Python that wraps up a result. The result may not be ready yet, but when you call f.result, it will be blocking until the result is ready. Then you can move on with the rest of the code. So ready doesn't necessarily mean successful. It can be an exception. Something may go wrong. It will still be propagated out of this f.result and will be raised in the scope of where you wrote f.result. So if there was a problem with the executor.submit POW, there will be an exception. Specifically, we'll see a runtime error later, and f.result will raise this runtime error inside this wait on future. So that is the introduction to PEP 3148. Okay, let's go on. Okay, why do we do this example? Very simple, but not simple at all. A one-line change can take a few months of effort. No reason you ever do this, but it's good for learning. The skills will transfer. And when you run this in Jupyter Notebook, you know Jupyter has a more complex system where there's some long-running loop, event loop that's there, right? So what you learn here may not transfer if you try to do this in Jupyter Notebook. I think about 80% of it will transfer, then the last 20% you have to figure it out yourself. So I can't discuss that here. Okay, this is the spectrum. So I will show a few files. There are 5 white boxes here. I have 6 files actually. The 6th file will be about the Heisenberg. So I split them into 2 rows. I will describe the first row first and then the bottom row when I demo. On the left side, it is 0% deadlock. On the right side, it's 100%. So I am pretty confident that the false deadlock code will be 100% locked. I am not confident that the no deadlock is 0%. I think I just haven't seen it. I haven't run it enough to see it locked. But the relative order of these items should be pretty accurate. And I will run the code to demonstrate how I reason about that. Okay, so there are 6 files that I mentioned just now. This table shows you on the left column what are file names, on the right column what are the behaviors. So again, it is not really in the spectrum order. So the first 3 are no 0% to 100%. The row 4, discourage, is closer to 0. The row 5 is at the right most, it's 100. Row 6 is no lock. And then there are some details at the bottom I'll talk about later during the demo. Am I demoing? Yeah, I should be demoing now. Okay. So I'm gonna get out of here. I'll run some files to see what does no lock or sometimes lock look like. So here I got a file. This file is exactly what you saw in the PEP 3148 just now. I'm not gonna describe it more. The only new part is the import, because in the PEP they did not import. So here we must import the ThreadPoolExecutor, otherwise it will not run. For the second line, I imported this thing. This is for debugging purposes. I need to do this so that I can look into the thread.py module. And this thread module, I am watching it under this watch pane. So I'm watching what is going on inside the module. I will talk about the watch pane and the call stack in more detail later. Import time, I'm just copy-pasting this imports throughout all the files. So I am not using the time here, but they will be used in the other files later. So I'm going to run this file now, Python, no deadlock, run, nothing. So why nothing? When you see the prompt returned to you, that means this code executed successfully. So let's just run a few times to feel more confident. Maybe if I run this 1,000 times, it will suddenly lock, so I don't know. But based on my experience so far, no matter how many times I do this, I can't get it to lock. I'm not sure if you can automate this process, because if you try to do a loop, right, the loop exists inside a Python function. But what I'm doing here is outside a Python function. So you may need to use shell tools if you want to rerun this again and again without pressing up, enter, up, enter. Okay, so that's no lock. Now let's go to the slightly more extreme one. But before we go there, let's go to sometimes deadlock. So what's the difference between no lock and sometimes lock? Let me go down a bit. The only difference is there's one line. You see line 7? Disappearing, appearing, disappear, appear. line 7. I just added a print. Added a print before the submit. Let's see what happens now. Python. The print normally should not do anything, right? Sometimes deadlock. Okay, this means no lock, no lock, no lock, lock. So that's what lock looks like. It doesn't give you back the prompt. So that's 3 versus 1. Let's do this a few times and count the statistics. So 3, no lock, 1 lock. Again. 4, 1, 4, 2, 4, 3, 5, 3, 5, 4. It's quite balanced. So that's what sometimes lock look like. Why is it locking? I don't have a reason myself, but I can say that line 7 is changing the timing of something. I will talk about what that something is later. There are two control flows that we want to think about. And now I'll show you always deadlock. What is the difference between always and sometimes? Okay, look at this. We got a 6 to 11 is the same. The only difference is 16. In always, I added a time.sleep. In sometimes, there is no time.sleep. Now, I'm going to run always. Lock. Do it a few times to convince you. Lock, lock, lock. Okay, pretty sure it's always locking. Okay, so now that I've gone through the demo, let's go back to the slides and talk through some theory of what's going on. Maybe a bit slow. So I'll try to go in more detail of what the objects mean. So I have two diagrams here. There's a time axis in the middle going from top to down. The green boxes are the workers. So that's the max worker equals to 1. The left white box is the executor's queue. So each executor has one queue where it stores work to be done. Inside the queue, there is this object called wait on future. It's that yellow box. When we start from the first row, there are 3 rows on the left side. The wait on future is put into the queue during the executor.submit in the main scope. And next, if you go down to the next step, the submitted wait on future will be moved from the queue to the worker, and you start working on the worker. And then while the worker is executing the wait on future, it will try to submit the POW onto the same queue. But then, so that's row 3 now. You will see that in the red box, I said the POW is not even submitted to the queue. There was a certain runtime error that prevented this code called workQueue.put. So put is an API where you put things on the queue. This put is not run because of a certain variable I haven't introduced yet. It's a Boolean variable that controls whether the executor has been shut down or whether the interpreter has been shut down. So on the left side, the scenario is the Python interpreter has been shut down already. It cannot put any more work. So although there is no lock, it seems like no problem, right? But a huge problem here is that POW is not even submitted. The work will not be done. Okay, on the right side, I'm going to describe how deadlock happens. For the right side, on the first 2 rows, it's still the same behavior. But on row 3 now, the shutdown variable is false. So it hasn't shut down yet. So we can put the POW on the queue. So in the wait on future function, when you do executor.submit POW, that thing will get onto the queue. So that's why you see the row 3 in the right side. And now the issue is when we do the f.result inside the wait on future, it is waiting for POW to finish. It's waiting for POW to finish. But POW is waiting for the worker to finish. Worker is waiting for wait on future to finish. So there is a cycle. None of them can finish. Let me close the cycle. Wait on future is waiting for f.result to finish. F.result is waiting for POW. POW is waiting for work on future. Okay, so there's a cycle there. And one major issue is we are having one worker. So that's where the lock happens. Okay, debugging techniques. I don't think I want to spend time here. So you can read these slides later because we'll be demoing the debugging. And right now, we'll really get into the meat of how to debug this, where the breakpoints are, how do I step, what do I look at. And let me go back here first. There are 4 pointers here, right? We will mainly be focused on the watch window and the call stack, not the debug console or the variables. So, no, not yet. Okay, now I'm going to show you how do I debug so you can see where in the code the theory I mentioned shows up. Let's go to the no deadlock case first. I have breakpoints at 14 before submitting. I have breakpoint at 7 before submitting also. So I will be saying what I press. Here I will press F5 to start the debugger. No deadlock case. It's supposed to pause at my point. This is a setting you can set as debug inline values in your preferences, and it helps you print the yellow part, so you don't have to be typing prints in your debug console. So it's stuck on submit. Now I'm going to press F10, so step over, so it will go inside the submit, and we'll see how does the main submit wait on future. Before I go in, we should look at the call stack also and the watch variables. So in the call stack, there's nothing interesting to see here. These 2 items here are because of debug.py, which is the mechanism that VS Code uses to debug Python. We will see more things here later as I go in. And in the watch pane, I have many variables printed here. It is fine to see all these errors because what you see here depends on the scope of where you are. So right now, it looks like a ton of errors, but once you step into another space, the errors will disappear and it will actually show visible values. So some of these things are actually looking at the same object from 2 different scopes. Like if I'm outside here now, maybe you can see thread module.shutdown is false, right? I can see it because I did that import on top. But if I get into another scope, then this false will probably become some error. But those errors will become readable. So I have 2 windows into the same object from different scopes. Okay, now I'm going to step in. F10. It jumps into the submit method of the ThreadPoolExecutor. And remember, this is the outer submit. This is the mains submit. This is not the wait on futures submit. Okay, I'm going to go F10, 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 and look at how does the max worker equals to 1 get started. Okay, these shutdowns are quite, we'll focus on 168 later, the shutdown. That's where the runtime error and the Heisenberg will come about. Okay, so here you're creating an item, and 175 is where it puts the item onto the queue. And after you put it, then the thread can take things from the queue and work on it. So focus on 176 now. The call stack will change after I step over. This is the place where it will start creating threads to work on items. So focus on the call stack. Boom. So you see that? Just now there was nothing. Now I have a main thread and a ThreadPoolExecutor. The ThreadPoolExecutor 00 is a default name. You can name it whatever you want. Main thread is the main thread, ThreadPool is the child thread. Usually, to learn this thing, you want to load more step frames, open everything up, see it. So you see that you're in a submit, and it's the submit of the thread.py. And for the executor, you want to see what it's doing. You may want to open it up also. But for now, I think there's nothing interesting to see in the executor. So if I continue stepping, it jumps back to this with. This with is called context manager. Why is it not getting out? Why is it still at context manager? Because the context manager has 2 parts internally. It has a double underscore enter and a double underscore exit. So it lets you define behavior before you enter the context and right before you exit the context. So right now, it is pausing to run the exit code. Right? Just now, when it paused here, it was waiting to run the enter code. So these are 2 different states. So if I continue stepping F10, it will get out and finish the submission. This run globals is the debugger thing. We don't need this. So shift F11, step out. Shift F11, step out again. You will see the call stack of the main is reducing because I'm stepping out. Okay, now this is the important part. Reminder again, we are on no deadlock case. This Python exit is a handler, it's an exit handler. So these kind of things are run when your Python script ends, it exits. So these are like the last kind of cleanup that you want to do before something ends. And in here, it is setting this shutdown equals to true. And this shutdown equals to true will affect whether we can submit later. So I'll show you the second submit later. So let's go down here. Shutdown equals to false in the watch pane. Second row in the watch pane, shutdown equals to false. If I run this now, the second row turns from false to true. So that's how you use the watch pane. Okay, let's continue going. Nothing interesting here. So it's gonna do some shutdown operations. I'm gonna, okay, right now we are at the inner, we are at a work on future. So right now this work on future is gonna try to submit POW, but it will fail. So let's see what's going on. If I F10, it's gonna go in. Again, we jump back to the ThreadPoolExecutor that you have seen already just now while trying to submit the work on future in the main. But right now we are nested, so we're trying to submit the POW inside work on future. Okay, go in, nothing happened here. There'll be a difference here. Remember, shutdown was changed from false to true, right? On the first try, it was false, so it skipped this. Right now, it's true. It will go in and raise this error. And that's why we see no deadlock. This whole code just dies. The POW never got submitted. Right? You see, it never went to 175. It already went out at 169. So if I run this, it's going to get out of this context manager. Then waiting, maybe I press some more. Okay, the rest of it is about some cleanup stuff. So I will F11. Yeah, and you see my prompt has returned. So that's the no deadlock. And now let's go to always deadlock. Go through that debugging process again, and we see where it goes. So same process, always deadlock with a time.sleep. I don't think I have time to demonstrate this, so I'm gonna jump ahead a bit. When you sleep 0.1, let me explain the theory. When you sleep 0.1, it's not enough. In the debugger world, clock still runs. So when you put the 0.1, that's too little. When you debug, you probably take 1 minute to do it. So while you're debugging, right, to the code, it thinks you're not sleeping at all. So to make the sleep actually have an effect, you need to sleep long enough. Make sure that while you're debugging, the sleep is still active. So here I put 3600 means I'm sleeping for 1 hour. Definitely I'm not gonna stay in the debugger for 1 hour. So it will have an effect. Okay, so let's go, F5. Submit the outer one, go in, nothing interesting to see here. Go in, get out, shift F11 to get out. Now, nothing interesting to see here also, go in. Okay, this is different. Just now we went to Python exit, right? After 15, straight away jump to Python exit, change the shutdown from false to true, then we go inside the wait on future and see the POW fail on submit. So now, what happens when you sleep? See, let's go, F10. Okay, that's the difference. There's a critical difference. It doesn't exit anymore. It doesn't go into the exit handler. So shutdown will not be set. It jumps straight into the submission. So if I F10 again, now it is trying to submit the nested submit. You can confirm that from the call stack also. You can see that the submit is in the ThreadPoolExecutor 00. It is not in the main thread. That's how you differentiate also which submit is going on. So let's go F10, and okay. Why is my screen keep jumping? Right? See, this is a different behavior. Because when you press F10, both the main thread and the child thread will change from the pause on step to running. So when both are running, VS Code is a bit confused like which screen should it show? Because when you press this play, right, all the threads on the same process will be playing together. They will all be racing together. That's where the race happens. So, but the VS Code is smart enough to know that it jumped me to the other screen, it jumped me back automatically. So right now you can see shutdown is false because we never ran the Python exit. So this variable was not edited, which means the runtime error will not raise. It means I can continue going and successfully submit the POW. So it's gonna put this W, which is the POW, onto the queue. And what happens after that? Okay, let's continue going. Okay, getting out of the context manager now. Okay, this is the first time ever where we went past line 8. Why just now cannot go line 8 in the no deadlock case? Because inside the line 8, it raised a runtime error. So you know when you have an exception, everything else will not run after that. this is the first time we went to 11. This shows that you have successfully finished the whole execute.submit POW function. So let's go in and see how does result behave. Okay, I think it didn't go in because I have no breakpoints inside the result. So I should have pressed F11 to go in, but if I press F10 and there's no breakpoints inside, it will not go in. We don't have to go in also. The theory here is that f.result will just keep waiting for the result of POW, but POW is being blocked by the worker. So there's only one worker going back to the PowerPoint, right, on this thing here on the right side. You can see that the yellow box is always there, so the POW cannot go in, it's blocked. So that's what deadlock looks like. And that's the full trace. Okay, let's go back to the big slides now. Here is exactly what I just said in text form, so I wouldn't spend more time here. Now let's go to this tweaks. We talked about first row of that spectrum. I'm going to the second row of the spectrum. How to discourage means push it closer to the left, 0%. How to force, push it closer to the right, 100%. Let's go to the code again. So let's go to, okay, this one I'm going to close it, discourage. What is the difference between discourage and sometimes? So I'll go to the left, I'll select sometimes, and I'll select discourage. Shift or control? Shift, no, control select. Sometimes. Okay, right click, compare selected, compare selected. It's a bit hard to read, maybe because of the screen resolution, is it? Yeah, I think it's because of screen, it's a bit hard to read, so let's not do the compare. I'll just describe what happens. The only difference here between the sometimes and the discourage is that you have another line 16 here. So you can see what we're trying to do in 16, right, is to shut down the executor earlier. So we try not to allow the POW submit to work. And I'm going to run this discourage to show you the behavior of what discourage looks like. And we do the counting exercise again. Discourage deadlock. Okay, this is a 1 no lock, 0 deadlock. 2 no lock, 2 0. 3 0, 4 0, 5 0, 6 0, 7 0, 8 0, 9 0, 10 0, 11 0, 12 0. Am I running the wrong file? 13 0, 14 times to get 1. Yeah, this demonstrates that when you see no lock, is it? It's not yet, right? 15, 16. Okay, am I doing something wrong here? Discourage deadlock. 17, 18, 19, 20. Finally, 23. 23 times. Okay, got it. Okay, you need to be a bit crazy a person to do this kind of exercise. You just need to not take things at face value and just keep banging your head on the wall. 23 times, 24 times, you got it. Okay. At home, I do it, it's less than 10. It's just live coding magic. Okay, so I'm going to go to the next one, force deadlock. How does force look like? Only difference is f.result. So to do an f.result, you first have to get a handle of the f first, right? So previously, line 15, we did not assign the executor submit to the f. Now you just assign it, hold it, and then so that you can wait for the result. You will see that this is permanent blocking. Always, or force. Force. Okay, block, there's nothing interesting here. I'm pretty sure that you will always block based on the theory and based on stepping in. There's nothing to see here. It will keep blocking. So why does this keep blocking? Because now you are stopping Python exit from running, so it cannot set the shutdown. Why is Python exit not running? The Python exit will only run when your main script finishes. When you put the f.result here, it is not able to finish. It will block until this outer submit finishes. But this outer submit cannot finish because it's waiting for the POW. Yeah, so this is the deadlock case. So why do I put this on the right side of the spectrum compared to always? Because these two guys are still sleeping. So it is not as deterministic as f.result. F.result, there is no time. It's infinite time. This one is still finite time, so it's weaker. The stronger lock is the f.result. So in your code, you shouldn't play with times. You should really use all these blocking mechanisms and synchronization mechanisms. Okay, let's go. I think we have 5 minutes left. Let's see how far we can get. Runtime error, the Heisenberg unswallow. Okay, so this is a situation where I want to see the runtime error, because when I first saw no deadlock, I'm thinking, is everything normal? It doesn't feel normal to me. If there's an error, why am I not seeing it in the main code? So I want to see this error. So let's go to the code now. Runtime, unswallow runtime error. I think the starting state, let's comment out everything, and this state is, and just running and see. Is it the sometimes? I think this is the sometimes case. Yeah, it's the sometimes case. So my first response, how do I see the error? Remember I mentioned the theory is that when you do f.result, you will get whatever errors happen inside a function's body, right? So what I was trying to do when I uncomment 17, is that whatever error happens inside wait on future, I want it to show up on line 17's f.result. But the problem is that this is the observer effect. I try to see the runtime error, but now I can't see it because it's going to block forever now. This is the false deadlock situation that I just showed. Okay, it's blocking, so I can't see it. How does runtime error appear? Runtime error appears when the Python file exits and it sets the shutdown to true, which makes the POW submit not submit and go into the runtime error path. But because I add a result here, then it's not going to go to Python exit. It's not going to put shutdown to true. It's false. So POW is going to submit. There will be no runtime error. That's the observer effect. Cannot see. You want to see it, then you add this, cannot see. Okay, so how do we solve this? One more thing. So the beautiful thing is that this is exactly what we saw in the 2 previous exercises. Line 16 was added to make the to create the discouraged deadlock file. Line 17 was added to create the false deadlock file. Put these two together, you can solve the Heisenberg. Okay, let's run this. That's exactly what we want. Now you got this. So I'm going to scroll up to show you what you have here. This is what I wanted to see. Okay, let's go on. Got a lot more material. Okay, how do we solve these problems? Let's see if you can see this. Can't see, right? Okay, let's skip this slide. I'll go to the next one. This one is the text form of the 4 solutions. So look at the columns. There's a file name. It's on GitHub. Key idea is more important on column 2. Column 3 is pros and cons. So it's just something you need to go back and revise or understand deeper. So I'll focus on column 2 first. Column 2, increase worker count. And the green part is the line of code that you need to change to solve this problem. So the solution 1 is the simplest. You just change 1 worker to 2 worker. Because there are 2 workers, you will not try to block. I mean, the queue, the POW on the queue will not be waiting for the single worker to finish wait on future. You will just go to the second worker straight away. So that will solve the problem. Solution 2, separate process pool. So instead of using the same executor inside wait on future, you change it to a process pool executor instead. Right? So you don't use the same ThreadPool executor anymore, and then this will solve the problem. Even if the process pool has 1 worker, it will solve the problem. Solution 3, external queue. This is really hard to explain. I can't explain it with text. We have to see the code, so I skip this. Solution 4 is not really a solution. It's just like sweep the problem under the rug. Okay, once second is up, it's not my problem anymore. Bye. So it doesn't solve anything, or it just return control back to your main prompt. Let's go on. So here we go to why do you want to do nested concurrency. So I have 4 rows on top, columns of outer and inner. So what we have just now was row 1's pattern. Outer is ThreadPool, inner is ThreadPool. But of course, in this kind of real life use cases, you don't want to use the same ThreadPool. If you use the same, then you must not put max workers to 1. You must put something more. If you put something to the more, will it also deadlock? I'm not sure. You can try that for the next PyCon. 2 workers, can you lock it? And then so the use cases are web scraping, batch processing, compute upload, and machine learning on SOMs. You can ask GPT to generate the code to help you understand and really run it on your laptop. And then I think what's more important to understand is why does something work or not work. So why not flatten? What do I mean flatten? Flatten means you don't nest. Means you don't try to create an executor in an executor. You just try to create one level of executor. These are the 4 reasons why sometimes you cannot do that. Because information may not be available to you all at once. You have to do the outer layer executor first before you get something that will control how you start the inner executor. So this is an analogy to this is like in object-oriented programming, right? Let's say an example could be scikit-learn. Scikit-learn is a machine learning library in Python. You would have certain information during init, but you will not have all the information that you need. Then you have some other information during the .fit method, and that's the data that you have. So there's a separation of passing data to the object. Firstly, you want to initialize it, and then maybe at an unknown time in the future, you have the data. Then you give it to the fit. So you cannot give the data to the init because you don't have it yet. So same theory here, you may not have the data that you need to just use one level of executors. So we need to nest. Okay, what else can you learn? This is a ton of CS concepts. Quite advanced stuff, so you can read this. That's why I love this example, because it relates to so many things. 6 here and 4 examples here. And bonus will not be talking about this also. So bonus is a summary of the 2 different types of shutdown. So one shutdown is the interpreter level shutdown. It's in Python exit, which is saw during my debugging. The other type of shutdown, you also saw it, is the executor's shutdown. It is of a smaller scope than the interpreter's shutdown. There are 2 different shutdowns here. And then also what I showed you is not the usual way where people code, right? Because I didn't use a context manager. So usually people would want to use a context manager and they start the thread with ThreadPoolExecutor so that all the errors are automatically handled and the executor is automatically shut down. So this is like an implicit way to do the shutdown. But there's a difference between what you saw during my talk today and the with. The with will do a shutdown wait equals to true, while what you saw is wait equals to false. So there's a tiny difference. Some frequently asked questions, I won't be explaining this also. How to know where to put the breakpoints. So if you have not much experience in debugging, this 2-line guide should be helpful. And also how to know whether there is a deadlock. Right? There's a theory here called the halting problem. You cannot predict whether there will be a lock before you run it. You can only investigate while it's running or after the lock has already happened. Then you use certain tools to figure out what's going on. So on the next page, what are the tools? Fork handler is a built-in in Python. There are OS level tools, strace and BPF compiler collection tools. So they are the Linux kernel tracing tools. And then there's this Python deadlock detector. I think the code base hasn't been updated for 5 years, so I don't know if it still works. But we can try. Anything is better than nothing. Okay, here are the resources. What else is interesting here? Okay. Point 5 is a book that I recently wrote, the one I mentioned. Quite proud of it. 15,000 words. My longest article ever. And then some of the other stuff are LinkedIn sharings, similar to this topic. So if you want to learn about synchronization, multiprocessing, race conditions, pipes, synchronization primitives, algorithm design, all this stuff is here. Then I think line 12 is quite special. It's published recently only, in June. So in Python 3.14, we will get the no GeoPython, no global interpreter lock. Some people ask me during interviews, what is global interpreter lock? So that is something that stops your multi-threading from doing parallel compute. So if you try to do compute work starting multiple threads, there will only be one piece of compute that's happening at a time. This geo problem is irrelevant when you do multiprocessing because each core has its own GIL. So there's no talk about fighting for GIL. Right? So it's a problem with multi-threading. And this problem may be gone soon in 3.14. All right, it's about me again, and then that's the end of our talk. Thanks a lot for attending.